Okay, this is section 8-6. This is recording number 1. All right, so this is just a couple of miscellaneous topics, additional topics, okay? The first one here I think is worth talking about. There's the relationship between confidence intervals and hypothesis testing. Okay, now what we are going to talk about is the relationship between confidence intervals and two-tailed hypothesis testing. If you have a two-tailed hypothesis testing like this, okay, so you got potential for the test statistics to end up here or the test statistic to end up over here. That's a two-tailed test like we've been talking about. That type of a test, that hypothesis testing type of a test, has a relationship to the concept that we discussed previously of confidence intervals. Okay, so what he's saying is there's this relationship between the confidence intervals and the hypothesis testing. There's this Tweedledee, Tweedledum. I mean, if you have one, you have the other. Okay, if the null hypothesis is rejected in the hypothesis testing situation, if you have a two-tailed test and you reject the null hypothesis, let's suppose the null hypothesis is that the mean is equal to something. Okay, the mean is equal to 10, the mean is equal to 12 or whatever. Okay, but you reject that hypothesis. Well, the confidence interval for the mean using the same level of significance will also not contain the hypothesized mean, right? Because if you're equally confident, if your confidence level is the same for the hypothesis testing as it is for the interval, you're equally certain. And what you're saying when you're rejecting the null hypothesis is you're saying, hey, that mean is not part of my interval. It makes more sense. Okay, so here's a typical scenario, a typical problem. It's a metaphor. We're talking about sugar being packed in 5-pound bags, okay? And the inspector thinks, well, you know what, I'm not sure that it has 5 pounds in there. You know, that's a legitimate question, right? You don't know whether there's really 5 pounds in there or not. So what he does is he does a random sample of 50 bags, so n is 50, and he comes up with an x bar. He comes up with a mean of 4.6, has a standard deviation of 0.7. Okay, is there enough evidence to conclude that the bags do not contain 5 pounds as stated on the label, and we're going to have a alpha of 0.05, so our error budget is 5%. So then they also say, well, let's find the 95% confidence interval for the true mean and then assume the variable is normally distributed. So we can do all of our nice easy tests, okay? So the very first thing we're going to do is we're going to test this concept, or test the hypothesis that mu is equal to 5. That's my null hypothesis. That's my status quo. That's what I think is true. Okay, that's what they say, so I'm going to assume that it's true. Our alternative hypothesis is that mu is not equal to 5. Okay, so here's the thing. We don't have a standard deviation for the population, so we cannot do the testing of the means using the z-score. We have to use the t-score. So remember how we did that? I think that was section 8-3. So we've got to come up with our alpha is equal to 0.05, degree of freedom of 49. Okay. Okay, let me backtrack. I had a little technical difficulty here. So we use the degree of freedom is 49, right? And then it says, well, then it says use degree of freedom of 45. Well, why do we do that? Well, if you look at the tables that we have, we don't have a 49. This is the t distribution. We don't have a 49. It goes from 45 to 50. Okay, so we don't have a 49. So somewhere in the book, he talked about this and said, well, if you have to use something in the middle here, you use the smaller number, I think is what he said. Okay, so in any event, we've got the appropriate table. We're going to find the test values. The critical value first. The critical value is 2.014, and is symmetric, so it's negative 2.014. So where did that come from? Give me 1 second. Okay, where that t-value comes from, that critical value, t-value, comes from this table, the t distribution. We're going to use 45 as our degree of freedom, so that's the appropriate row. What's the appropriate column? Well, it's a two-tailed test, and we want it to be 5% for the alpha. Okay, so two-tailed alpha 0.05, this is the right column, so we come down and come down, come down till we get to the appropriate row. You got to use your fingers here, and it's 2.014. Okay, and then the t distribution is symmetric, so it's that number plus or minus. Okay, and that's exactly what the author has right here, plus or minus 2.014. So those guys, those are my critical values. Then I compute the test value, just like I did before in section 8.3, I think it was, 8-3. Here's my test value. Here's my test statistic, oftentimes is called. You write down the formula each time, put in the numbers, this is what you get. Negative 4.04. So that's way the heck over here. So since it's so far over from this critical value, clearly we're going to reject the null hypothesis. Okay, so we make a decision, we reject the null hypothesis. Okay, all right. So what we're basically saying is, hey, listen, you know, you can advertise that it's 5 pounds, but I did the test. I went ahead and I sampled 50 bags. And I didn't come up with even close to 5 pounds. I didn't come close to 5 pounds. I came up with 4.6 pounds with a standard deviation of this. There's no way that you would expect to get a random sample of 50 bags giving you a mean of 4.6 if the mu is 5 pounds. It's not going to happen. You know, you're lying to us. It's not really, on average, is not 5 pounds. Okay, so that's what you're saying. That's by this hypothesis testing. What you're also saying, however, is that, hey, listen, given this same information, I can calculate the 95% confidence interval for the mean. Here it is. And do you remember doing this? It's been a while. This is the formula. The mu that I'm going to calculate is the x bar plus or minus the margin of error. Here's the margin of error. Well, we already have everything we need for the margin of error. We have the t values, the critical values, the t's. Okay, that's right there, 2.014, negative 2.014. Okay, we've already got those. So we've got that, and we've got the s, we've got the square root of n. So we multiply that out, and that gives us our margin of error. So what we're saying is that mu, our best estimate for mu, the interval, is the x bar, which is 4.6, that was given to us, plus or minus this margin of error. So that's telling me that the mu is between 4.4 and 4.8. Well, if the 95% confidence level for the your interval estimate is between 4.4 and 4.8, well, 5 isn't in there, is it? The mu is somewhere between 4.4 and 4.8. Therefore, 5 is not in there. This is where it's at, okay? So that's telling me that the confidence interval of mu does not, oh, here's a typo. The 95% confidence interval should be of mu. Of mu does not contain the hypothesized value of mu is equal to 5. Hence, there is agreement between the two hypothesis tests and there's an agreement between the hypothesis test and the confidence interval. Okay, I hope that helped. You know, the math is not that hard. It's the language. It's how hard it is to say these things. You know, it's like, you know, the math, the symbols kind of tell you everything you need to know, but it's hard to say it, in my opinion. Okay, so hog weights, another example, is basically the same idea. It's going to be the same thing. You're going to do a hypothesis test, and you're also going to do the confidence interval to estimate what the mu is, and in this case, the mu, the confidence interval does contain the hypothesized mu of 200. See, it's inside this interval. So therefore, we do not reject the null hypothesis. So you can do it either way, you get the same result. That's what he's trying to say. And then what he's also saying is, hey, this really only works for us for the two-tailed test. This relationship can exist, and you can figure this out. However, it's a little bit beyond the scope of this text. Okay, so the next thing we're going to talk about here real quick is about this type 2 error. Okay, the type 2 error, the concept is that you decide to not reject, but you should have. The null hypothesis is false, but you did not reject it. That's called a type 2 error. And then there's a concept called the power of the test. Okay. Right here is talking about the power of a test. I'm not going to test you on that, and you don't need to do any of the quiz questions on that at the end of the chapter. I just would suggest that you have a chance to read that over, just so you know that it exists. There's just so many permutations to this whole situation that I don't think it's worth trying to learn a superficial evaluation of it. Just know that it exists, so that if you ever get into this kind of work, you know that you need to go look it up. Okay, and the idea behind this is that the power of a test, I'll get a definition for you. Talking about the power of a test is 1 minus beta. So just go ahead and read that. Just know that it exists, but I'm not going to ask you to handle that on an exam. Okay, so that takes care, believe it or not, it's a long chapter, that takes care of chapter 8. So chapter 8, is what it all boils down to. This is hypothesis testing. We can test for mean and proportion and standard deviation. And the concept is we're trying to decide, is the null hypothesis, is it supported by the evidence or is it not? And in chapter 8, we're comparing a sample to the population. In chapter 9, we're going to be comparing a sample to a sample. So in Canvas, I think I used the examples. I said something about that in chapter 8, we're comparing a sample to the population. So as an example, I said, let's take a sample of children, let's feed them Wheaties, let's see how many push-ups they can do. That's a sample that you are going to, that'll give you an X bar, and we're going to compare that to the population mu. And we're going to say, do these kids, after eating the Wheaties, does this sample of kids eating the Wheaties, does that give them the ability to do more push-ups than the population can do? That's chapter 8. Chapter 9 is you're comparing two samples. So you have somebody that uses brand A and somebody that uses brand B, and you compare the results. Does brand A do a good job or a better job or a worse job than brand B? And whatever you're testing, it can be cavities, it can be blood pressure, it can be pulse rate, whatever it is. But you're not looking at a sample compared to a population. You're looking at two samples compared to each other. So that's chapter 9, and we're going to get to that next, obviously. Okay, well, thank you very much. I hope you enjoyed the videos.